For today's meeting, we're going to start looking at algorithms that solve stochastic games, which we had talked about when we introduced the multi-agent reinforcement learning problem. But when you start looking at game theory, you just look at normal form games where there's this payoff matrix. Here it's just showing a general sum game for two players and two actions where there's two numbers in each of these boxes, and the two numbers just represent what reward value each player gets corresponding to this outcome, this joint action. So this is like a 2x2 matrix corresponding to all of the different 2x2 action selections that the agents could take place. Now we'd like to extend it to a situation where we have multiple states, like is shown here, and then each state is its own game. But now, these numbers now represent the immediate payoff or reward that the players would get for the decisions in this state. But then there's a transition into another state, possibly, with its own reward values. And in this case, like if this is a game that goes on forever, depending on, what the policies are of the two players, there's some expectation of how these transitions occur and future reward values that the players will get depending on what state they end up in. So now the situation is more complicated because just like in ordinary reinforcement learning, the immediate rewards are not the only thing that matters. It also matters all the future rewards that a player could end up accumulating. And then that's why we have to look at algorithms that try to estimate not just this immediate payoff matrix, but something equivalent to it that tells us, what are the relevant rewards for the player depending on the joint action, accounting for all of the future things that could happen in the game. And, when we had looked previously also at a simpler case than a general sum game here, like for two-player games, there would be two different, you can either think of it as, one reward matrix with two values, or here I've written it as two separate matrices with, corresponding values for the X and Y player. But in a zero-sum game, the rewards are always defined to be the negative of each other for each player. So the sum of the rewards for any outcome in the game is always zero. This would be like a game like rock, paper, scissors, where there's three actions and for each player. And in that case, either it's a win, lose, or draw for each player, but the rewards always are set up so that the sum is zero. And for today, with these algorithms, we're only going to look at the case of zero-sum games because there's a nice property these games have, which we had derived in one of the previous meetings, that there's this minimax solution, which is unique. And, this is showing an example of it for just a simple 2x2 game. But the minimax solution is the solution such that each player is using a policy that is the best response to the other player simultaneously. So there is no deviation either player can make from their policy to yield an improvement for them. And the nice thing about for zero-sum games is that this is a unique joint. Each player has a unique policy, which is the minimax solution, and there's a value associated with it, which would be, the value that the first player would earn in the game that they would expect to earn. And then the value for the other player would just be the negative of that. And there is also, for the minimax solution, a linear programming solution that we can write. And actually, this is what's shown in the book. Is this linear programming solution to actually, make this something practical that we can use with most like packages that would solve linear programs. It's helpful to convert it into something to do a change of variables, where here this program is like directly solving for the X's, which would be the action probabilities for each player. But it's helpful to do a change of variables where we compute these values and then we end up normalizing these to get the policy once we've solved the linear program. And this way, we can actually write it as a maximization over this sum. So this is, the minimax solution is an equilibrium solution for zero-sum games. Now, other types of games, like general-sum games, have other types of equilibrium solutions, like the Nash equilibrium that we had talked about. And the Nash equilibrium is also a case where the players are locked in sort of a mutual best response. However, the problem with the Nash equilibrium is that they are not unique. And in the case of games, and also they're difficult to solve for, there is no simple linear program that can just find a general Nash equilibrium for a game with multiple agents and multiple actions. So because the Nash equilibrium is not unique and it's also difficult to solve in the first place, it introduces a lot of problems. Although all the algorithms we talk about, you can apply the same algorithm if you have a way of solving for a different equilibrium, like the Nash equilibrium. But, we're going to look at the minimax solution because this one is actually unique. So we know that it exists and it has a clear answer for the particular game we are looking at. So chapter 6 is what we are talking about. And this chapter, introduces like the first foundational algorithm for coming up with an equilibrium solution for a game like this, which in this case is actually going to be an exact solution that, we have a way of checking that it is converged to the exact solution. And this is the same type of algorithm that we saw with ordinary reinforcement learning, where we had the value iteration algorithm, which was a way of calculating the exact solution for the optimal policy for a single agent acting in a Markov decision process. And now we have this other version of value iteration for stochastic games. And here, the way they've written out the algorithm, they kind of hide all of the game theory stuff that's important in this value step, because the intention is for this algorithm to work for general equilibrium solutions for games. But if we're looking at a game, a two-player zero-sum game, then this value corresponds to the minimax solution. And in that case, these m's represent an estimation of what the payoff matrix is for a particular state and a particular player, like 1 to n. But in the case of a minimax game, we only need one of these, because all these estimates for the second player are going to be the negative values of what they are for the first player. So this step in the algorithm will just consist of evaluating the minimax solution for this game, like we did here. Like if we have this linear program here, like the reward matrix would be a 2x2 game. But now these values are not just going to be the reward for that game state, like the actual reward the environment gives for this state, but are also going to include these future state values. So here, like this step in the process looks a lot like what we do when we calculate Bellman updates for value functions, where this is saying, we have a value for A, which is this joint action that the agents would make in this particular state. And this R is the payoff that each agent gets, all of the I's get. Here it's being computed for one of the agents. So normally for a game, we don't have to compute this because all of the information is contained within the payoff matrix for the game. But here we're adding the discounted value of the transition state, where now this value is something that, has been computed in this part of the algorithm, where it's taking whatever our current estimate is of the game values here, and then computing the equilibrium solution in that state. So these two processes occur over and over again until the whole thing converges. Because once the m values and the v values are correct, then this update will no longer yield any change. Because it means that all of the values we have in m are actually the correct values accounting for all the future transitions that occur based on all the future joint actions. And it's assuming that both players are going to try to achieve this minimax policy. So just like with normal value iteration, it all rests on the idea that when this process starts out, these things are not equivalent. But we know from the Bellman equations that, well, at least in single agent reinforcement learning, we have this result from all the Bellman equations that when the values are correct, then this recursive relationship should be true. And here, it actually involves two different pieces. It's not just the values, right? Because we're computing the state values for each agent, as well as these m values, right, which are the payoffs for all the different joint actions. And the reason we need both is because we need to use these values to compute the equilibrium solution, which in our case is going to be the minimax solution. And also, unlike ordinary value iteration, where there's a note of it here, but when we look at, if this wasn't a game where there's joint actions, but we're just looking at a single agent taking actions, doesn't have to account for the behavior of the other agent, then this whole thing ends up reducing to just taking this max operator, where we just look at the max of this value over all of the actions that the agent can take. So this always will result in some deterministic policy, or it could be stochastic, but only in the sense that there could be multiple actions that have the same exact value. So we could, choose either one of those or, split our probability between them. But these equilibrium solutions we're going to compute, like the minimax solutions, because they're looking at these payoff matrices, can end up being stochastic policies that are like truly stochastic, where we could have some arbitrary probability assigned to certain actions. And that we'll see when we look at a specific game example is going to be key in distinguishing this from what value iteration looks like when we look at the single agent problem. So here, I'll show, actually, before we get into more the details of these algorithms, we're going to be using a particular game example throughout this discussion, just mentioned in the book. So I'm just going to jump ahead a little bit to this example here, which is an example of one of these stochastic games where now there's not just, a single game like reward matrix here, but there's a lot of states, and each state, we're going to have to actually calculate what these expected reward values are in different states. So this is a simple multi-agent problem that we can easily frame as a zero-sum problem. Unlike the previous multi-agent example we had, which was the level-based foraging example, that's more of a cooperative game. This is a competitive game where there are two players on this grid. And for every time step, the players can move in one of the four directions, up, down, left, right, or they can stay still. So there's 5 actions in this game. And at any given time, one of the players has the ball. In this case, this is like sort of a very rough analogy for a soccer game. And the idea is that, each agent has a goal that they are trying to score in. So like player B is trying to score in this goal and player A is trying to score in this goal. And the players move, and if a player successfully moves into the goal with the ball, then the game ends, or the episode ends in this case, because we're talking about multiple steps, where each step is like a normal form game, individual game with the joint actions between the two players. And the thing that makes this game, like an actual game instead of something we could reduce to a single agent problem, is that the two agents make their actions simultaneously, right? So this is not a turn-taking game where one player gets to move and then the other responds. Both players make an action selection simultaneously, and then they move simultaneously. And if during the course of their turn, both players like collide, or like one player attempts to move into the space that the other player currently occupies, then they lose the ball to the other player. But the other little wrinkle in this is that how you decide whether a player loses the ball or not, it does depend on sort of which player moved first, even though they move simultaneously. When we look at, if there's two players, like if A was here and B was here, and they both try to move into this square simultaneously, right? So B goes right and A goes left. Then how do we decide, what happens, who gets the ball? And it kind of depends on who sort of randomly got lucky enough to make the move first. So if A was selected to move first, then A would move here, B would attempt to move into A and lose the ball. So this is a stochastic game, in that like the actual transitions are stochastic between the two players because of that probability of who moves first. But there's really only two possible outcomes, right? Like if not for one player going first, there would only be a single outcome for every joint action. So, even though it looks like we might have to write this game down or model this game as something where we just sample transitions, we can actually write the game down with the full probability distribution of what happens after joint actions. And I have the game. So I added this game to my notebook here that has these environments. So for this soccer game, like the states have the positions of the agents, and then which agent has the ball. And then just for other things being easier later, it also contains the width and height of the sort of the playing field, so that we know if a player moves out. And I think the only time a player's allowed to move into the goal area is if they have the ball. Otherwise, that move just keeps them in the playing field. And then we have this step function, which takes the state, and then A1 and A2 correspond to this, like the joint action of both players. And then there's just two possible outcomes to a step. It depends on whether the agent 1 was allowed to go first. So this is just a true or false flag. And then, using this step function, we can either make an environment where the steps are random and there's sort of this 50-50 chance of one of the players moving first, or we can make an environment here where, in this case, like when we have a environment where the entire probability distribution is specified for transitions, we can just write down a map for the reward and state transitions, where we just see exactly what the probabilities are of each thing happening. And in this case, can see what it looks like. So these are like these transition maps here. So the state transition map. And here, because there's these multiple probabilities, this is modeled as a sparse vector where, like, in this case, for this transition, there is only one state that it ends up in. Because this issue of which player goes first is only relevant when the players are close enough to collide with each other. If they're not close enough to collide, then it truly is deterministic. And then here's an example where now there are this 0.5 just corresponds to the 0.5 probability for each of the transitions happening. And then these are the two states that you would that could be transitioned into. And same, the reward values are going to be mostly 0, except in situations where one player has a scoring opportunity. So yeah, this is what the game looks like. So I have this. Oh yeah, I also added this. So there's this utility now to run an episode for one of these stochastic games where this run function takes the game, which is like whatever the stochastic game is that you've defined. And then by default, it will just use random policies for both players. But then if you've actually trained a policy that you want one of the agents to use, then that would be passed into this. And then that would be used by the agent during the episode. So just to get things started with this, so here I'm going to be using this soccer environment and the version of the environment which has all of the transition probabilities in it. So that way we can actually use this. I'll go back. So this algorithm, it's mentioned in the book, but actually none of the results in this chapter use this value iteration algorithm because this requires summing over this transition function. And these are the probabilities. If we don't have these probabilities, we can't use this algorithm, which is also true in ordinary reinforcement learning. So the soccer environment usually would be written as just a sampling environment, and we wouldn't have these. But since I have it in this form where I have the probabilities, we can actually test out this algorithm as well and see what the results look like. The probability. So the transition probabilities are not, these are not predictions of the future. Like these are actually just based on a single step forward in the game. So the game knows once a joint action has been selected. So this would be like both players, decide what action they are making. And then from that information, we know the exact probability of each transition happening. So like I'll start showing like concrete examples of this, but like if a player is in a scoring position and they move like into the goal to score, then that would be like a probability of 1 that they would, that they would get a reward and that the game would be over. So usually these probabilities are 1 in this game. The only time they're not is when it's split in half, when there's a conflict between the two players, if they're both trying to move into the same position. And that's what creates, the 1/2 probabilities. So we can create a random policy for this soccer game. So in this case, there are 5 actions. Here, actually, wait, did I show? Oh yeah, so here are the agent. So there's 2 agents in this game, right? 2 agents competing against each other. They each have 5 available actions. And these actions are available in every state. So if the agent tries to move off of the arena with an action, it's just treated as like a no-op action. So it doesn't actually matter. It can select, one of those actions and it won't. It'll just stay within the bounds of the arena. So this just means that in every state, there's this 1/5 probability for every action. Okay, so what we can look at is now like, what does it look like when 2 random players interact in this game? So that's what I'm showing here. So player A will be blue, player B is red. And then if a player has the ball, it's just shown as like a solid black circle inside. And then it's an open circle if they don't have the ball. And then A is trying to score in the goal that's labeled blue, which is on the left side, and B is trying to score here. And the game will also start in one of 2 random states. So it always starts with A and B in these positions. And what's random is there's a 1/2 chance of each player having the ball at the start. So they'll sort of alternate with the ability to start with the ball. So here, this is going to come up later when we actually show like solutions with policies. But the way I'm displaying the policy is these are just all the actions, and the opacity of the arrow is just like how much probability weight that action has. So this is what it looks like when there's a 1/5 probability for every action. And then to the right is the actual action that was chosen on this step. Okay, so for every step of the game, we can see like what the policy is for the player and then what action actually occurred. So because these are both random policies, any one of the actions could occur on any step. We can see this game, because these are both random, these games can take a while. Actually, first, maybe we should look at the statistics here. So, not surprisingly, when you have two random policies, the win rate, this is showing the win rate from the perspective of the first player. In this case, they're both random, so it doesn't really matter. But, it should be 0.5, right? Anything other than 0.5 is just going to be some kind of sampling error. So essentially even, and the average, actually, wait a second, yeah. So I've also allowed this to run for long enough that there are no draws. I consider it a draw if it reaches some cutoff number of steps without either player scoring. So we can see the average number of steps is about 100, which, makes sense if they're playing randomly. And then we can also see like a little more information about this. So if a player starts with the ball, they actually have, like a plus, like they have a 10% advantage versus not. So like they'll win like 55, 56% of the time compared to just 50% of the time. And, that makes sense, right? Because if you already start with the ball, then there's a higher chance of just randomly scoring without getting interference from the other player. But, it's not that much of an advantage because, again, they are just moving randomly. So we can see some examples. We can just advance this to a point where player A gets the ball, which let's see how long it takes for that to happen. It might occur. I don't think it takes too long. We can see they're just moving around randomly. All right, every time I run this, it'll like regenerate the episode. So I had one before where it might have changed hands. Oh, here we go. Okay. So let's see if we can make sense of this. So here we have player B has the ball, and player B attempts to move down, right? Which actually is into the space of player A. Now, if player A took the no-op action where they just stayed in place, then they would actually guarantee getting the ball. Because regardless of who went first, player B would be moving into their space, right? Now, what happens is player A actually attempts to move right here. So if A moved first, then A would end up here and B would end up here. And there would be no exchange of the ball. But we can see what happens is because in the game, player B actually moved first, or like the way the calculation of the moves occurred, is that B first attempted to move into the space that player A was still in, and therefore lost the ball, and then doesn't end up moving at all. And then player A ends up, receiving the ball and then taking its desired action, which was to move right with the ball, right? So that's an example of where, the move order affects the outcome of both where the players end up and who has the ball. So does that make sense to everyone? So so now player A has now lost the ball again because moving into the space of player B. Here B was attempting to move up, which it can't do, so it just stays in place. So this would always result in the same outcome, where B gets the ball and neither player moves. So if they end up sort of being stuck next to each other, these exchanges can happen back and forth a lot. And then we can see an example at the end of what happens when a player wins. Yeah, so here, A ended up close, in one of these two positions, these two scoring positions, and then just randomly decided to move left, which results in the episode ending. And the outcome is that, A gets a reward of +1 for scoring this. Does that make sense to everyone? So, like, the random policies are not that interesting, right? But we can at least see sort of how long it takes for certain things to happen on average. So now we can actually look at the value iteration algorithm. And a portion of this algorithm, so this function here, solve minimax game, this actually is to do this step in the algorithm. So this thing that just says value here, this is supposed to compute the equilibrium game value. Now, to actually run this algorithm, we don't need the policy for each player, right? Because this isn't actually using a policy to select actions. This is just iterating through all of the states and all of the joint actions. However, when you calculate the minimax value, you end up needing to solve for the policy anyway. And also, when we're done with this algorithm, we're going to want to actually get the final policy out for each player. So this actually ends up also updating the policies, right? So this is like, once you have the reward matrix, which is the payoff matrix for a non-repeated normal form game. So this is like solving the game from the perspective of, it's not caring about the fact that it's a stochastic game. All the information about the stochastic game is contained within the reward matrix. And these are values that are going to converge over the course of the algorithm. So once they've converged, it is as if in every game state, we just have a unique game which has these payoff values that could be played like a game without actually looking at any of the transition states. And from that single game, we can compute this equilibrium solution. So we need to populate the reward matrix here with this M. So remember these M values here, right? These are values for every joint action and every state, right? So we can actually, here I'm representing it as this three-dimensional array where I'm pulling like the final dimension is the state dimension. And then the first two dimensions are one for each of the joint, for each of the agent actions. So like the joint action is this 2x2 space. And then the final dimension is the dimension for the state. So what this does is, this is kind of left over from what I had covered before when we looked at minimax solutions. But this version of the function sets up the model to do the optimization. But because I'm going to be repeating this over and over again in the value iteration algorithm, I've set this up so that these constraints, so this step, this is adding the constraints in the problem that depend on the reward matrix, which is being populated here from the current, M values that are going to have to converge over time. But, and then this part of the algorithm, this computes like that recursive Bellman value, where we take the reward and then the value at the transition state, right? But again, like these V estimate values, these will only be the correct values when the algorithm has converged at the end of it. So here is the full like value iteration algorithm. The reason why I have to set up two different models here for the linear programming is that even though we only need one of these to compute the game value, which is like, right, we can, because the value for the second player is just the negative of that. The policies actually don't correspond to each other. Like each policy could be completely different, and we need to compute each policy separately, even though we can get away with just having a single set of value estimates. And because it's a zero-sum game, we're just gonna, if we know that we're computing it for the second player, we're just gonna take the negative values of this. So this is gonna sweep through all of the states. Well, actually, so this is computing through all the state transitions, and this enumeration here is effectively enumerating all the states and joint actions, right? But this is like sort of a three-dimensional space because it's both of the joint actions. I'm sorry, like both of the individual actions, enumerating through all of those, and then also going through all of the states themselves, right? So this is like a 3 different indices here represented by this. So this sweep goes through all of that to compute the values. And then we go through all of the states, right? In this case, now this is just like an enumeration over states, not the actions. And then for each state, we then compute the minimax solution for the current state and these M values right here. Like we're always populating these M values for the joint action in the state. And then we have to actually compute the minimax solution, which is also going to update the policy for that individual agent, right? But we only have to actually solve the first model here because we don't actually need the second agent's policy until the end after everything's converged, which is what I do here. At the end of then when this whole thing is converged, right? I'm keeping track here of the delta, right? So these are the state values. I guess it doesn't actually make that explicit in this algorithm, but you do this update for each value, and then you're checking to see how much the values are changing over an entire sweep of the state space. And when the largest value update is less than some threshold, then you know that you've converged to something. So that's what's being checked here. I'm keeping track of this delta max as the max of all these the difference between the old values and the newly updated values. And then, yeah, at the end of everything, then we can then compute the policy for the second player. So, yeah, like structurally, it is very similar to how we do value iteration in ordinary reinforcement learning. But the big difference is having these M estimations, which are, basically going to hopefully converge to the true game values. We can see here the result of running this. Actually, wait, yeah. So here's the result of running this on the soccer game. I put in a given, sort of decided on this threshold after running this and seeing, because this is this linear programming solution that occurs inside of this, I don't have as much control over how this operates or what the tolerances are. So when you do normal value iteration in reinforcement learning, you can really get the convergence to be really good, like almost close to machine epsilon. In this case, because we're solving a linear program, it's a little messier and it's hard to get tolerances down to like 0. So I found like this tolerance is pretty reliable. It also depends on how you scale the game, the rewards in the game. Like you can wind up in pathological situations where there's values that are too close to each other and the linear program has trouble converging. But here, this has converged. to at least to this tolerance. And now we can see the outcome of this is that we have these values. So this game happens to have 840 states, which, depend on where the players are and who has the ball. And enumerating over all of that gets you 840 states. And then these are the resulting policies. You can see whenever we have a policy where this column corresponds to the policy for this state. And if there's a 1, it means that it's a deterministic policy. If it's 0.2, it just means that it's uniformly random. And then we'll see there are other states where it's neither of these, and it's something stochastic in the middle. And then these matrices, so each one of these slices here, like this is the game reward for state 1. And you'll see we'll have one of these for every state. So this has now converged to something where we can treat this state as now an ordinary game, a zero-sum game, where this is the payoff matrix. But now this payoff matrix is accounting for all of the future moves from both players following the minimax policy. And these policies that we've computed are computed based on these game rewards. And we know that these are all the correct minimax values because in the algorithm, because we've converged, now all of these values are equal when we do the update. So all these things being equal verify that this is the correct minimax solution. So now that we have an exact solution, right? Like this, the nice thing about this is that we'll see later an example of computing this with sampling, where we don't have an exact solution and we have to collect samples from the environment and estimate these values. But because this is like an exact solution method, like in theory, we can keep iterating this and get the values to whatever tolerance we want, then we can like actually see what the optimal behavior is for both agents in this game. So first I'm going to show this table. So again, like because it's the minimax solution, we would expect this to be the case where there's like a 50% win rate. The whole point of this is that both agents are behaving optimally against the other one. Now, this happens to be a game which is an even game. Like there are other zero-sum games where one player would have an advantage, and in that case, the solution, like the actual value estimate would be positive for one player. Not the case in this game because the game is totally symmetric and there's a random chance of the players starting in either starting state. However, what is interesting is that notice that this solution, the minimax solution that it's found, is one in which the player that starts with the ball actually has a 2/3 chance of winning. And, similarly, a 1/3 chance if you don't start with the ball. So this is not a situation where the players are sort of locked in a stalemate. They're trading off the chance to win, but because they know that there's an equal chance of either player getting the ball. Now, if this game was set up so that one player always started with the ball, then this solution would be different. And actually, I'm sorry, so actually like the minimax solution would be the same because it doesn't actually care about the starting state. But if the game was such that one player always started, that player would have like a permanent advantage in the game. And the value would be like this. So what I'm showing here is the win percent, the loss percent, and the draw percent in this case isn't relevant. And this is the average number of steps for episodes. And then this is the actual thing that the minimax policy is trying to optimize. So in theory, this is the best reward value. Now, this is the expected value of the discounted reward, which in this case, there's a discount rate here of 0.9. Now, the solution to this ends up looking different if you treat this as an undiscounted problem. By setting this to 0.9, there's two ways of thinking about this. One way is that you take 0.9 to like let's say you win the game in 5 steps. Then instead of getting a reward of 1, you get a reward of 1 times 0.9 to the 5th power. So we have an incentive to win faster. That ends up being equivalent to if the problem wasn't discounted, but if there was a 0.9 chance of the game ending on every step. So like imagine, just there's a 10% chance every time you make a step in the game that the game's just over. And that also creates an incentive, like if you have the ball, that you would want to score quickly because you may have some chance of scoring. And even though there could be a risk of losing the ball, if you do that, there's also a chance the game will end before that bad outcome happens. So either way, you create a situation where you have some incentive to actually do something with the ball, right? If we had this as an undiscounted problem, then it's not really a well-posed problem, actually. And you end up with both players just holding the ball and not moving because there's no incentive to actually move forward, because there always is some risk. Like we'll see that the way the players compete with each other, there always is some risk. Like there's no risk-free way of taking the ball and scoring if the other player is optimal. So because of that, if the problem wasn't discounted, you would just want to hold the ball forever and not try to do anything, because that would be no worse than actually trying to score. But in this case, we can see that, with the ball, if we do take the risk, we have, a 2/3 chance of winning, and also winning in a short enough number of steps that it actually is worth our while. This now is displaying the minimax policies playing against each other. And we can actually see what strategy they employ, like how much risk they take, which is really does depend on this discount rate. We could maybe look at a future time about how the policies actually meaningfully change if we adjust the discount rate, because it's also possible that this value of 0.9 makes it convenient to compute things, but that it doesn't actually fundamentally change the policy. I think I did experiment with this a little bit, and this property of the 2/3 win rate with the ball, I don't believe change. It seems to be somewhat fundamental to how this problem is structured. So also, so what I'm showing here is, again, like the policy and the action for each player. And also what I'm showing here is the actual reward matrix for the game for this state, because this is one of the things that's learned by value iteration. And then these are the two corresponding policies to this reward matrix. So like what's being shown here is for the B player, what the minimax solution is for this game state. So like, let's say this wasn't a soccer game. This was just a new game I just handed to you. Like this is the payoff matrix for some arbitrary game. Then these are the minimax solutions for this game. And we can see that for this game state, there are two deterministic solutions. So for player A, the optimal value action is down, right? This 1 here corresponds to the down action. And we can see why the down action is selected by player A. And it should be that the worst case scenario, if we look across here, right, the worst case scenario is this negative 0.218. And this worst case scenario should be less bad than any other action selection. And it should be pretty clear cut. Like here, the worst is worse. And if you look at every row, there's a worse outcome for A, because we're assuming that the competing player is going to be right, choosing the worst outcome for us, which is then the best outcome for the opposing player. That's the property of the best response policy. So let's see. So this is a 6-step game won by B. B starts with the ball. So we can see like what does A try to do? So, I mean, first of all, B kind of, as we'd expect, tries to move to the right. A sets itself up in a blocking position. And now we're actually in a state where the minimax policy is not deterministic, right? These are now stochastic policies, and they're not like 0.5. There's two actions favored, but it's actually probably these values. If I had to guess, I would say this, because of the tolerance I've selected, these maybe haven't converged to the exact values. It's possible this should be like 2/3 and 1/3, 1/3 and 2/3, but it's also possible that the true values are like 0.65 or something. And most games, especially games with more than just two actions, the minimax policy is something stochastic, because if you select any one action consistently, that's something that could be exploited by another player. And the point of the minimax solution is that there is nothing that can exploit it. And right, like it is always the best thing you could do, assuming your opponent responds the best way. Now, it doesn't necessarily exploit other players fully, but it shouldn't be possible to do anything to to win consistently against the minimax solution. And in order for that to be true for most reward matrices like this, you have to employ some sort of randomness. You can see this very clearly in something like the rock, paper, scissors game, which is a very simple game. Everyone knows how it works, but you could imagine that if you picked one action consistently, then there's always a corresponding action that can beat that. Whereas the minimax solution in that game is to select all actions with a 1/3 probability. And that is the only way that you can guarantee that your opponent can't find a way to exploit you. It doesn't mean you'll win every round, but it means that there's nothing your opponent can do, on average to actually to beat you. So we can see here that player B, sort of hedges between either staying still or moving up. Right now it's being blocked. There's no point in B trying to move to the right. And then player A also hedges between moving up and moving to the right, getting into a blocking position. And right, the only way this is a minimax solution is for both of these things to be true. Like, both players have to be aware that the other player has this stochastic policy. Otherwise, there would be something that one of the players could do to get a permanent advantage in this position. So we can see what actually ended up happening is both players appear to have selected the more likely action for them. So now A moves to the right, B moves up. Yeah, and now, player A again moves to block. And so now, because these are both deterministic actions, both players now know they're going to end up in this state, right? And I guess the point of ending up in this state is now, like, A is trying to create a situation where it's blocking, and there's going to be a situation where B attempts to score, and there's a chance to steal the ball. And because of the way this game is set up, and there's sort of an equal chance of a player being able to move before the other player, there's a player can always create a situation where there's basically a 50-50 chance for them to end up with a ball and thus get an advantage. At the same time, that could fail, and then they would be in a very bad position where they would get scored upon. We can see what happens here where, they're both, like, we could sort of see how in this situation, if either player had a deterministic policy, then you'd be able to, it would be exploitable by the other player. Like, yeah. But in this case, they both actually have the same policy, where they either stay in place or go down. And now, depending on where they end up. Okay, so basically what A is trying to do is create this situation. And the only way it can do it is by randomly choosing between staying still and going down. Right, so there's a chance for this to happen. There's also a chance for both players to just stay in place or to swap positions. But if they end up swapping positions like this, now, we see why there's this. We've created the situation where one player, because of the discount rate, is attempting to win, even though there's a risk of losing the ball. And actually, we can see the value here. Right? This value is the game value for each player. So from this position, player B thinks the game value is 0.38, right? Which is actually not that high of a value. Now, it's actually higher than the average value, right? So this is an advantageous position overall. But if it thought it was going to score in the next step or in the next two steps, then the value would be more like 0.9, right? So this 0.38 and then the negative 0.38 does have a significant chance. This corresponds to a 50% chance of losing the ball and then needing to, regroup and try to steal it back on the other side. But the risk it incurs from that bad outcome is actually far enough in the future that it's still worth it to attempt this. So this is now deterministic, and we can see that player B is going to try to move into scoring position, and A is going to try to, steal the ball. And this is now just a coin flip, and B ends up winning this coin flip, right? So A tries, A didn't get the coin flip win, so now it's stuck here. And now we could see that the value is 1 because it now is guaranteed to be able to score on the next move. So this is a case where B started with the ball and then was able to just win. And if we rerun this, oh yes, we can also see this deterministic outcome. Can we see why? Yeah, so like this is a game matrix in this state, but this results in a deterministic outcome where here, right, this is the worst value, see, negative 0.385 here. So the reason why this is chosen is because this is the worst case outcome. And similarly, we have, it's actually both like this row and this column, right? It's this point here. So I'm sorry, there's a question about if. Yeah, so these policies were not actually trained by samples being taken, right? This whole algorithm just converged to the minimax policy for both players. So we'll see, I will answer this question to see that the way this game and most games work is that if a player has to follow a deterministic policy, then there's always a way to exploit it. And that's the problem with solution techniques that don't use game theory concepts because they can't learn the type of stochastic policies like this. Like we'll see, not in this state, but like really where you see it come out is like this state right now. Even when we get to here, right, this is a stochastic policy, but you see it's 0.5, 0.5. There is some chance that even something that just learns action values, like probably not, I mean, this 0.5, 0.5 probably is the result. Like you probably couldn't learn this from action values, but you could do this if you actually learned two action values that were like, had the same exact value at these two states, and then it just happened to work out. But in general, like these stochastic policies that we end up with, like these ones, are not, but the one I showed before where we had, oh, sorry, I actually reran. So I generated, did I generate a new episode here? I don't know, but oh yeah. So this state, right? This state has learned a policy, which is the result of solving this game matrix. And you're never going to end up with these values if you don't, actually calculate an equilibrium solution based on the correct game matrix values. So if we rerun this, we can see another example. Let's see, so this B. Okay, so here's a case where now B starts with the the ball. And because this game is won by A, we know that, so A, okay, so they end up, right? So now A creates the same scenario as before. But now what's going to happen is A is going to win the coin flip. See, so B tried to move into scoring position. A was able to block it. And now A is going to wait for B to move off. And then we'll see what B, so B should then try to do the same sort of thing. So A waits for them to swap vertical positions, then decides to move. Right now, again, there's this game of like waiting for the stochastic situation where they happen to swap positions. And now actually we can see that A already is going to try to do the same thing that B tried to do here. But this move where it tries to get past B could actually occur at any one of these positions. Like either way, it's a coin flip where if A wins the coin flip, it's able to just move to the goal. And we can see that if A ends up here and B's here, B has no way of stopping it from reaching the goal, right? So this sort of swap attempt could occur at any point on the game field. So here you can see A, again, wins this coin flip. And now this value of 0.81 just means that it's guaranteed to score in the next few steps, right? So now it's just able to go over. And even though it looks like B, like once B is in this position, even though like, you know, the way the linear program is solved, like there's actually nothing B can do. So here, B's, yeah, like we could see the, yeah, it has a value of negative 0.81, which corresponds to this. But see how all these values are the same across this row? So like now, if you ever have a game matrix where all the values are the same, now this is a trivial game solution because this doesn't actually, the response of B is irrelevant here, right? All these values being the same mean that regardless of what B does, A's best action is this. So this ends up actually reducing the joint action calculation into something where we could just look at, you know, already know what A should do from all these values being equal, and that these are all the, you know, the highest value. So yeah, then it just becomes a straightforward win for A. Yeah. So are there any questions about how the minimax agents play against each other?
I guess if there were more agents would it, you know, I'm just wondering if it would end up having the behavior basically being, you know, stay at the goal essentially forever in order to block everything.
You mean if there were like teams where,
Yeah.
like team A had two agents?
Yes.
I mean, you'd probably need a bigger field to do that, so there was actually room for everyone to move around.
Yeah. You
But
would still probably need a bigger field though.
then you would probably set up the problem where you still had only two agents, but the two agents each controlled all of the all the players on their team, and then you just had a much bigger joint action space. And no, I still think you would end up with this attempt. I mean, if you set a discount rate, you would still end up with some attempt to win. But I guess it really comes down here to the fact that if you have the ball, it's not that you still have only a coin flip chance of winning, even if you start with the ball, right? Because the other player we saw can always create a situation where they have a chance to steal it. But if you start with the ball, you're more likely to score in a shorter number of steps, right? Like you're incentivized to try to score if you can score in a few in some number of steps, and then the corresponding chance to get scored upon occurs many steps in the future, right? Because that's like worth less. And we can see here the trade-off creates this average value of like 0.2 for the player that starts with the ball. But on average, it's just 0, right? Because, you know, it makes sense, right? Like we have this is a symmetric game with equal chances, so like there is no way to consistently win in this game. But because of the discount rate, the players arrive at an equilibrium where they still attempt to win because they know that in the long run it all balances out, and they sort of exchange winning chances. But your losing chances get extended into the future, so you don't worry about it too much. So another thing we can evaluate now that we have the minimax solution is we can see how well it does against the random policy. Now, again, we haven't trained this specifically to be successful against the random policy, but we do know, because of the nature of the minimax solution, that it should do better. Like, it can't do any worse than it does against the other minimax solution. Any other policy we choose to play against it, it should do at least as well as this, if not better. And we can see against the random policy, it does quite well. So it wins 98.2% of the time, which is, again, is like because of the way we have a discount rate. The reason why it has some losing percentage is that it actually does take risks occasionally, right? Like it doesn't refuse to risk the ball, because in order to actually successfully score, you have to be willing to take the risk. Against the random policy, that risk taking is much more successful because the random player doesn't have the ability to exploit anything. We can see, again, starting with the ball, you essentially never lose, and then starting without the ball, again, because it's assuming it's playing like another minimax player, it does still get into those positions where it tries to steal, and if the random player happens to win the coin flip and move in the correct direction, which, occurs some amount of time here, it's not an insignificant amount of time. It loses 3.5% of the time. But, it takes a lot more steps. Now, winning, it essentially wins like in a straight shot here, because the random player is unlikely to block it. And again, like the thing that really, if we were to optimize this, the thing that it's actually optimizing is the discounted reward, which is not the winning percentage, right? This number accounts for how long it would take it to win and the chance of winning from different scenarios. So here we can see against this player. Here I'm showing the policy, the random policy of player. But this is an example where B starts, so B is now the random player, and A is the minimax player. And B starts with the ball, and then we can see what A tries to do. So A, interestingly, so in this position, this is a position it never gets into when it actually plays the minimax player. Luckily, the value iteration solution computes the optimal policy at every state. So there's no blind spots for the minimax player. But playing against the random policy, we do get to see its behavior in other situations. So this is a situation where it doesn't move when B is in this corner, because I guess any movement it would make would result in a worse position than just staying still. And now B is staying still. And now, right now that B has moved here, now A has a pretty complicated policy, right? See, this is, right now, the probability is split between 3 different actions here. But what we should see happening, oh yeah, interestingly here, weirdly, yeah. So again, the minimax player never actually ends up in this part of the field where it's down here, right? In order to score it, it does have to move up. So the reason why, like, it might seem like A should always move to the right or something, but here, it actually does have time to get into position here because of how low B is. So it has this, even a chance to go to the left here. This also, of course, depends on the fact that the minimax policy for B, which is shown here, this isn't what it's following. It's following the random policy. Also includes a chance to go left, in addition to right and staying still. But we should see eventually A get into the position. Now here A is assuming like the minimax player is that the minimax player is going to try to pass it here, which is why it tries to move down. Now, if B doesn't try to pass it like the random player, it's not actually bad for A. It's just that, the reason why it's down with 100% probability is this is the exact scenario that A creates in the minimax solution where it tries to steal the ball. We can see what's going to happen. So it's not going to end up happening. Here, it's going to try to block. So now here, right, A in this position does not expect to steal the ball, right? Because, oh wait, actually, I'm sorry. No, this is again the same position where A is going to assume that B is going to try to move right, right? Like the minimax solution for B is to move right to try to score a goal. And if it gets past, it has a guaranteed win. The random player after, 19 steps happens to actually do this and then lose the coin flip, and then A just, calmly wins in a straightforward way. We can see, though, perhaps another, yeah, so here's a case where A starts with a ball and then he just wins in 4 steps because the random player doesn't try to do anything intelligent. Okay, so now here's a case. This is something you'd never see happen in the minimax game, where this is now 42-step game won by A. I'm guessing that in this situation, A probably, yeah, so here A loses the ball, but then, because the random policy is not good, it tries to steal back. And let's see if it actually... Yeah, so here it's positioned itself to steal the ball back. But you can see it's going to take many steps for that to happen. But because the random policy is so bad, okay, so here finally A now here steals the ball in a manner that would never happen against an optimal opponent, right? Because A moves left, B should move up here. Instead, it moves right into A, and then A, surprisingly gets the ball and then has a straightforward way of winning. So that's against the random policy. We can say it wins. So 4 steps is really the minimum amount to win. So this average is 5.4, which means that reflects how often the random policy just happens to do the right thing and block A or steal the ball back. Yeah. So any questions about its performance against the random policy?
No, I did not have any questions.
Okay. Well, hopefully that's clear to everyone. So now we're going to get to this next algorithm, which is very similar to what we looked at with value iteration, but now we don't have the probabilities. And instead, what we have to do is initialize something, these Q values. These Q values are also, familiar from single agent reinforcement learning. Here, though, the A's are not the actions, but rather the joint actions. So these Q values are the same as the M values we had up here. Wait, where is it? For value iteration, right? Because these are a value for each state, each agent, and the joint action. And these are the things that we use to compute the equilibrium solution. So here, we're going to compute the Q values with sampling. So now we're going to be in a certain state in the game. We're going to initialize the game in a state. Then we're going to either choose random actions for the individual agents with some probability epsilon, or we're going to use the current Q value estimates at that state, consider it to be here, a game matrix. So this is what I was showing here. where like this is the actual game matrix. So in this joint action Q learning, we're going to be having estimates of these values as we're sampling from the environment. And then once we have these estimates, we can use them even if they're wrong to compute these minimax policies. And that's what occurs here in this step, this value. So really what we need is the minimax. Well, we need both, but once we solve the game, we're going to end up with the values and the policies, which we're going to use to sample actions. And this update step, it combines the two different steps that occurs here, right? So here we have the step where we use whatever our current value estimates are, and we update the M values, and we alternate, going through the states and actions. And here we actually make use of these permanently saved values for the game states. In this case, we're not saving two sets of things. We're not saving the values separately. We're just computing them every time we observe a transition state, and we're using the Q values to get them. And because we're observing a sample from a particular joint action that was picked, right, this ends up being a sample of what this value should be. And we're going to maintain these estimations of the game values, right? Where now there's a unique value for every state and joint action, tuple, which for this game with two agents is this, 3 different indices. And because this is, like, the reason why this is called joint action learning with game theory is that we are saving joint action value functions other than in ordinary reinforcement learning. We just have action value functions. And here, like, an individual agent, J, is going to have estimates for all of the joint actions, right? So this isn't including just its own actions. It has estimates for the outcomes of its own actions combined with the actions of other agents. And it's only through having these joint action values that you can actually compute the game theory solutions, like in this case, the minimax solution. But because we're using sampling here, right, this now has an issue where we don't actually know if we've converged. We're not, in general, sweeping through all of the states. So we don't have this same like check we can perform in this algorithm where we can actually see if any states are still changing in value. Like, we don't even know how long it's going to take to, in general, get to all the states because we're relying on sampling them and using this, exploration parameter to get through. So, but, we can still write this algorithm down. These models, like, this ends up actually looking exactly the same as what I had for value iteration. And then, so this is the part of the algorithm where we either select a random action. So here, this version of the algorithm is only for a zero-sum game. So we know that we have 2 agents, and we also know that the reward values are, just negative each other for, agent 1 to agent 2. So when you run this algorithm, right, we're actually like going for some number of steps. So here we're iterating through, and we can cap it either by the number of steps or the number of episodes or both. And we actually initialize a state, using, hopefully the game environment, provides some, in the case of the soccer game, we have those 2 initial states that we could randomly choose between. And then we end up either randomly choosing an action for each agent with the same probability, or we actually sample the action from the policy for that agent, where the policy is actually being computed by the same thing that we use to compute the minimax solution in value iteration. So here, this is like the same. But now here, if we compare this to what the value iteration algorithm looks like, right? So here we had solve minimax game. And you can see all this is the same. So here we have the M estimations we're using for the game values. And yeah, these values are computed with the use of this Bellman update. And in the Q learning, we don't have these. Instead, we're using the Q estimation. And then if we go back to that, the Q values are also, the only thing that we're updating in this. Yeah, so here's like, we're using this target value. This game state value is used for the part of the value update, right, where we have to add the discounted value of the future state. But here, instead of going through all the probabilities of future states, we are just using this st+1, which is the next state that we actually end up in after taking the joint action. And because of the way this is calculated, notice that we don't actually need to have access to those probabilities, right? We're just, once we observe the joint action, we observe the next state, and then we're able to calculate this as an expected, or not as a sample update rather than an expected update. And we have some learning rate here, alpha, which is like a step size parameter. And in general, for this to converge, we have to keep sampling and have some probability of sampling all of the joint actions and states, which is why we have some probability of choosing a random action. And then this learning rate also has to decay. We can try to track the convergence. But, for this to meet all the properties of converging, this has to decay to 0 over time to make sure that the size of the updates is shrinking as these values get closer to the true values. So this will end up, we can use this algorithm to compute the same exact type of solution for value iteration, but in the case of games where we don't have access to the probabilities, right? Like to these transition matrices. So probably, we can probably stop here for now, and next time we can look at the results we get when we compute this solution, but with this joint action learning that uses sampling, and see, how much better or how much worse it is than the exact solution. And then we can also look at what types of solutions we get when we use algorithms that don't use game theory concepts. So in the previous chapter, we looked at algorithms that did single agent reductions. Like independent Q learning was one where we just throw the agents into the problem and they each attempt to learn their own optimal behavior in an environment where the other agents are training and learning. And that actually might not converge to anything depending on how the game is set up. In a cooperative game, we see it does converge and it's fine. But in this type of situation where we have a zero-sum game, that solution has a lot of drawbacks compared to something that actually uses game theory concepts. So I guess next time we can go over that, see how far we get, and then possibly move on to some of the other algorithms. But I think, yeah, this soccer example is actually pretty good in how it illustrates the properties of different types of solutions and, how they differ. So yeah, next time we'll look at the independent Q learning, how that differs, and then we'll probably have time to move on to some of the other concepts. But are there any questions about what we went over today? And also, I think the meeting next time, to look at the calendar, but let's see. Oh, the next meeting would be on January 5th. Yeah, that's fine. Okay, so yeah, I think we probably will just have the meeting on that day. It shouldn't cause any problems. Okay, well, if not, thanks for coming, everyone. Yeah, hopefully you can find links to the other relevant information in the meeting description. And yeah, see you if you come next time. Thanks.
Thanks, Jason. Bye.
Thanks.